Okay? Let's pray and we'll get started. Father, thank you for this day and for the spring break that we've had and the rest and the help and the success and the fun that you've given in all these things. We pray that you help us today as we start on the back end of this semester in chemistry and looking today at liquids. Help us to understand these concepts, help them to be clear. We pray this in Jesus' name. Amen. All right. So we're on liquids right now. Probably begin starting looking at just differences. And you're going to know this stuff. It's most of it. Not overly complicated, but looking at some of the fundamental molecular differences between solids, liquids, and gases, and why they are what they are. So, lots of just concepts and definitions to begin. So, you think about a solid, a liquid, and a gas, right? And so, in terms of where do we want to start? Characteristics of a solid, right? They have a definite shape, fixed shape, right? And the molecules are in close contact. Because the molecules are in close contact, you're looking at some kind of an that's between molecule, intermolecular force occurring pretty much for everywhere for every molecule, right? We're going to call them IMF, intermolecular force, just because it's a lot to write over and over and over again. So in a liquid, you do not have a fixed shape, right? You have no fixed shape. You have close molecules, and you have lots of intermolecular forces. And then for gas, you have no fixed shape. You have very distant molecules. And ideally, playing on the ideal gas law, right? Ideally, no intermolecular forces, right? Okay. The same molecule can change from a gas to a liquid to a solid. You think of water, right? And so if the molecule doesn't change, but the property of the gas or the liquid or the solid is so different, well, what accounts for that? It's going to be temperature, right? So if I were to go from a solid to a liquid, right, we would call that melting or liquefaction. If I were to go from a liquid to a solid, we call that condensation. Wrong one. Sorry about that.
Solidification.
Yeah, solidification. Right. Okay. If I'm going from a liquid to a gas, that's vaporization. And from a gas to a liquid is condensation. Another important one is at times we can go from a solid directly to a gas. And all of a sudden the word has escaped my mind. Sublimation. There's nothing worse than being on the spot and going, oh wait, it's not there, the page is blank in my head. Anyway, sublimation. So carbon dioxide is a great example of this, where it goes just from a solid to a gas, skips the liquid phase. Okay, it's not the property of the molecule that changes between these. It's not even the nature of the intermolecular forces that changes between these. It's the proximity and it's the speed, right? And so the closer they are and the less kinetic energy they have, the more opportunity there is for those intermolecular forces to come into play. And as they come into play, they will slow down or contribute to the slowing down or speeding up even. Okay, and so this is all temperature dependent. Capiche? Okay. So, oh, other factors here are pressure, by the way. Pressure is a big one. I didn't even talk about that. So, if I want to go from a liquid if I want to go from a liquid to a solid, I can do that by increasing the pressure. And the same holds true for a gas to a liquid, right? You can have you can take like a syringe and you can breathe into it, and you know that you're going to have water vapor in it, and then you compress that piston and you'll see water droplets begin to form. You do the same thing with a balloon or something like that, right? So if I add pressure, that's going to help me move from one phase to another, right? So that's another factor. And the opposite is also true. I can go from a solid to a liquid or a liquid to a gas by removing pressure. This is actually how like refrigeration works. Is they change the pressures and release temperatures and all that kind of stuff. We're not so worried about that right now. So, what we are worried about is types of intermolecular forces. You feel good on all this? Mm-hmm. This is pretty much all review. Mm-hmm. The one factor probably here to just make sure you do know is the pressure. Yeah. So intermolecular forces. We're going to be concerned today about a particular subset of intermolecular forces between neutral molecules, okay? So electrically neutral molecules. Is to say we are not worried about ions. That's a whole different ballgame. Okay. It's interesting how this works. I learned this back in my day different than it's covered now. Like really different. So I'm going, wait, that's not right, but we're rolling with it. So they're going to group all three of the intermolecular forces we're going to talk about as van der Waals. And I know that's Dutch, and I know it is actually van der Waals, but we're in America and we say things wrong and we say it proudly. So we're going to say van der Waal. Well, I can't even do it. Once I learned it right, it's hard to go back. It's van der Waals. Okay, so we're going to have three classes of these. And just to cover it real quick, the first one is going to be dispersion forces or London dispersion forces. Okay, next one is going to be, should be dipole-dipole. What they're calling it? They are, okay. Dipole-dipole moments or dipole-dipole attractions. And the third one they're going to refer to as hydrogen bonds. As I learned this was a subset of this, and this was a subset of that. And this was not that, but oh, there's an R there, isn't there? It's not. It's Dutch, not Spanish. Okay. So here we are looking at van der Waals. I got this brings back to where we're supposed to be. All right. I can talk about this and explain it much better than I can get it technical. Here's the deal. Electrons are moving around in a molecule in an electron cloud, right? And they're following orbitals, right? They don't just jump from a p to a d or, but within that p, they move, right? And we can't know exactly its location and its energy, all that at the same time. So it has certain amount of freedom as it's moving around. And it just so happens that every once in a while, you'll have that electron in a place that maybe you don't expect it to be, and you'll get a slight momentary charge. So let's look at maybe some methane here, okay? Right, so normally I think of an electron here and an electron here, and here we are, right? Of course, we actually understand it's more like this kind of a thing. What if, at a period of time, I just happen to have two electrons over here? Just because of the randomness of it all, they end up kind of two in the exact same. Now, we know this isn't going to last very long. They're going to repel each other, right? But for a moment, here they are. And this methane is it's compressed, it's under high pressure and low temperature, so it's in a liquid form, and it happens to be near another methane molecule. Well, what happens here is these electrons are going to repel these electrons, right? And so it's going to force them over to here, and now I've got my hydrogen, right? And it's, of course, the nucleus has a positive charge. But my electrons get repelled right here. Well, now for this brief moment, this gets repelled and these two act as a magnet. And it's also a cascading effect, right? As these link and as these get repelled, it's going to repel these, right? So I'm going to get this slight negative charge over here, which is going to induce a negative. When we talk about induction, it's the movement of electrons. So we get this slight momentary induction of electron motion and charge. It only lasts like that. And if this is the only one I have, it doesn't mean much. It's going to do and it's going to undo, it's going to flip, and it's not going to last. A single van der Waals interaction means almost nothing. Okay, it means very little. But then you get to the idea of like fats versus oils. And so these are huge chains. This is going to be glycerol, okay? Fats and oils are very, very similar, right? They're just these hydrocarbon chains. I don't have time for all that. I'm going to draw it like this, okay? Well, in something like a fat, these chains have single bonds throughout, and so they just zigzag back and forth, and I've got hydrogen sticking off everywhere. And of course, I would have these everywhere throughout my molecule, right? And so what happens here is when I have a van der Waals here, and I induce a positive charge here, and a negative charge here, and a positive charge here, and a negative charge here, all of a sudden this is linked to 2 molecules, or maybe it's actually linked to 4 molecules. And I've also got another one that's happening down here. And I've got another one that's happening down here. And as this keeps going, I may have thousands of these slight, momentary, temporary forces of attraction that have been induced, okay, through London dispersion forces. London's the guy who discovered it. Dispersion is just talking about, hey, it's about the dispersal of the electrons throughout their cloud, and sometimes they don't line up the way they should or stay because they have certain freedoms, and a force, because it's a force of attraction, it's an intermolecular force. It does all these things. But when I have hundreds or thousands of these happening, and it's inducing it in all the ones around me, well, that's actually quite a lot. It's like little bits of Velcro, like no one little hook and, hook and loop on Velcro, it works like this. So like, here's my loop, and I've got a little tiny hook that comes under. One of those means nothing, but I get millions of these, and I can wrap you in Velcro and hold you up against a wall, and you can't get off. It's the same way here. And so this is what keeps fats as a solid. Whereas an oil is very similar, but it has these big kinks, which the shape, the conformation does not facilitate as many van der Waals forces. And so it will be a liquid, even though they're very, very similar. This is going to be a solid room temperature, this is going to be a liquid, okay? I realize it did a lot more talking. Technically, what does it want you to know? Because the electrons of an atom or molecule are in constant motion, or alternatively, the electron's location is subject to quantum mechanical variability. At any moment in time, an atom or molecule can develop a temporary instantaneous dipole if its electrons are distributed asymmetrically. The presence of this dipole can in turn distort the electrons of a neighboring atom or molecule, producing an induced dipole. That's what we just did. I think that's better, but things you do need to know: larger and heavier atoms and molecules exhibit stronger dispersion forces than do smaller and lighter atoms. This is talking about atoms, not molecules, right? So the thing that you know about a big atom is that its valence electrons are much further away from the nucleus. It has a lesser hold on them, right? You think about ionization energies and things like that. Well, there's also just more freedom for van der Waals or London dispersion forces to occur. They're more likely to be asymmetrically distributed. So, you think about your periodic table, you're more likely to have London dispersion forces in all of a sudden I can't think. In bromine than you are in hydrogen, right? Mm-hmm. Because of where the electrons are at. So in a large atom, the valence electrons are on average further from the nuclei than in a smaller atom. Thus they are less tightly held and can more easily form temporary dipoles that produce the attraction. The measure of how easy or difficult it is for another electrostatic charge, for example, a nearby ion or polar molecule, to distort a molecule's charge distribution is known as polarizability. Okay, let's take a look at it. It wants us to just work through a conceptual problem. We'll do that. I'm going to erase this side, and then we'll talk about dipoles. Order the following compounds of group 14 of a group 14 element combined with hydrogen from lowest to highest boiling point. So CH4, SiH4, GeH4, and SnH4. So these are all group 14 elements. They all consist of a central atom bonded to 4 hydrogens. So what's going to be the deciding factor on which one, first of all, boiling point, right? You're going to have to escape from a liquid to a gas, right? You're going to have to escape all intermolecular forces to be able to do that, right? So essentially we're asking which one of these is the most readily going to have escape intermolecular forces, which of these is going to have the least intermolecular forces. And of course our factor that's going to come into this is the size, right? So
It's bigger.
the smallest.
CH4.
CH4, okay. What's second?
SiH4.
Third?
G. Yeah.
They give it to us in the right order. Yeah, they literally put them in the right order. Okay, great. So that's easy. So it would look like this. It would be CH4 is less than SiH4 is less than GeH4 is less than 10H4. Okay? Okay. One more sample problem. Order the following hydrocarbons from lowest to highest boiling points. C4H10, C2H6, C3H8.
So the lowest is C2H6. Then C3H8. Then C4H10.
Okay. Well, there we go. The shapes of molecules also affects the magnitude of the dispersion. Do we care about this? Yeah, there are other factors than just the particular constituent molecules. For example, we can look at C5H12. C5H12 is going to have a couple of different isomers. So these have the same chemical formula but very different structural formula, and this is going to go really along with the idea of the oils versus the fats, right? The shape matters. And so you get yeah, you get something like this. Right? Which one of these has the most surface area for these van der Waals to occur? This is neopentane. This is isopentane. And this is in-pentane. So which one has the greatest surface area?
Let's say the last one.
Yeah. And this one probably has the least, right? And so, so this is going to have the most van der Waals, the second most van der Waals, the third most van der Waals, and each of these would have a different boiling point, right? Based on that, even though chemically they're the exact same, each of them is C, what is it, C5H12? Yeah. Okay. All right. If you have time, go look at geckos and van der Waals forces. It's amazing. Really, really cool stuff. But we don't have time right now. Dipole attractions. Okay, so this has everything to do with electronegativities, right? So the more electronegative atom has a greater pull, a greater force on that electron. These were temporary, right? Differences in charge. A dipole is a permanent, it's a fixed charge, right? You think about water classically. Oxygen, greater in electronegativity, the electrons are attracted more towards oxygen. It has a negative charge, a permanent negative pole, and down somewhere between the two hydrogens, you have a permanent positive pole. What does it want you to know? The effect of a dipole-dipole attraction is apparent when we compare the properties of HCl molecules to nonpolar F2 molecules. Okay, what's the molecular mass of F2?
Maybe 36, 37, basically, because it's 18.998.
For F.
Yeah, for F, so times 2 is going
Give it to me again. 36 to 37?
to be, yeah,
36.5?
Yeah,
Okay. And for HCl?
36 to 36.5 to
Okay. So it shows these because these are, you know,
similar.
they're both diatomic. They both have a really, really similar molecular weights. Okay? So, but these have equal electronegativities, and these do not, right? So, as a consequence, because of the difference in electronegativities, this has a dipole-dipole moment, a fixed dipole-dipole moment, and so you're going to have a dipole-dipole interaction, which is going to prevent it from simply boiling away, right? And this does not, right? The only interactions that you can possibly get here are London dispersion forces, which are much weaker than dipole-dipole moments. And so even though they have the same molecular weight, this is going to boil away much quicker than that is, right? Let's see. Both HCl and F2 consist of the same number of atoms, same molecular mass, and same average kinetic energy given the same temperature. However, the dipole-dipole attraction between HCl molecules are sufficient to cause them to stick together to form a liquid, whereas the relatively weaker dispersion forces among nonpolar F2 molecules are not, so this substance is gaseous at this temperature. Okay. Next up is hydrogen bonding. So, hydrogen bonding, I need to not worry about how we talk about in biology. Let's talk about it here. So, hydrogen bond, well, okay, so here we're looking at the difference in,
That's really good.
erase my hook and ladder, or my hook and loop. London dispersion forces, we're talking about no difference, right? We get to hydrogen bonds, we're talking about the difference in electronegativities, but between very specific hydrogen and
Carbon.
nitrogen, oxygen, and fluorine. That's it. Those are the three most electronegative atoms that there are, or molecules that there are, right? So, of course, our increase, the electronegativity runs this way, right? Okay, so it's a bond between hydrogen and one of these is going to produce, it's a dipole-dipole attraction, but it is so great that it has its own name, right? Okay. Particularly strong type of dipole attraction, hydrogen bonding. Here's where it gets cool. I'm going to just generally fix. Okay, so let's do this is H2S. Okay. And then, okay. And then this would be H2SE. And then this would be H2TE, right? So if you look at your periodic table, right, we've got sulfur, selenium, and tellurium that are on top of each other, right? They're stacked, right? So we're within. Okay, then we've got HCl is going to be right about here, okay? And then HBr, and then HI, okay? There's a pretty definite trend there. I'll use a different color for the last one, okay? We've got pH3, and we've got astatine H3, and then we've got SbH3. I put this in the wrong place. This is supposed to be up here. Okay. There's a trend, right? But it doesn't hold true here. We would expect these all to be somewhere down here, right? Something like that. It would fit the pattern. But it doesn't. It doesn't because of, you know, here the trend we seem to see has everything to do with increasing molecular weight, right? Molecular mass, and these electrons are further away, so they're held less, so it takes less energy for them to boil, right? These would be smaller, they'd be held more tightly, you know, all right. But we see quite the opposite. These freezing point, what am I looking at here? Yeah, okay. So now what we actually see is here's H2O. Here's HF. And here's H3. And so the thing that's causing these to have such an increased energy required for the boiling point is the hydrogen bonds. It just holds them together so tightly. Right? Okay. So consider the dimethyl ether. Am I okay to erase this?
Yep.
All right, let's erase it. By the way, what time is it?
1:10.
Okay. How long do I have?
You have,
1:50?
yeah,
Okay.
40 minutes.
Pretty good. Never quite sure how long it's going to take. Consider the compounds dimethyl H3OCH3 and ethanol CH3CH2OH and propane, that's CH3CH2CH3. Their boiling points, not necessarily in order, are -42.1 degrees centigrade, -24.8 degrees centigrade, and 78.4 degrees. Okay, so this is going to require the most energy, right? And followed by this, followed by this. So it wants us to match these with these. Did I write them up there? CH3O, I can't even see that that's an H, that looks like CL3. CH3, and this is, sorry, these are poorly written. This is CH2. It's bound to be CH2. No, it's CH3. CH3, CH2, okay. All right, so what's our number one factor here?
I think the size, or
Okay, we got size, and what are our other factors?
the
Size and hydrogen bonds, right? Which is going to have a greater impact, the size or the hydrogen bonds?
I think the hydrogen bonds.
Hydrogen bonds. So which one of these is going to do hydrogen bonds?
It's the first and the second.
Let's think about how this one is. If we were to draw this, you've got CH3, right? O,
It's not going to be hydrogen.
CH3. So it's not going to be a hydrogen bond.
Yeah, the second
Right.
one.
This one, though, you're going to have CH3, CH2,
And
OH.
now it's
That's a hydrogen bond. And here, we're just going to have CH3, CH2, CH3. Okay. All right. So, which one do you think this one is?
This is the most one. 70.
Okay. So now we got to take a guess at these two, right? Well, these are going to, this section and this section are going to be the same. This section and this section are going to be the same. Our only difference is going to be here, right? Well, let's think about mass, first of all. What's the mass of a single oxygen? Or
It's
should be 16, right?
Yeah.
Okay. And what's our mass over here?
It's 12 plus 2 hydrogens, 14.
Okay.
It's
14? Yeah, I mean, it's pretty close, right? These could play a role here.
the electronegativity
Of
the middle.
the oxygen,
Yeah.
right? Could potentially induce more London dispersion forces. In which case, this would have less London dispersion forces, right? And so this would be potentially there, wouldn't it? And then this would be here. So let's see what the book has to say if we're thinking right. Shapes are all similar, so they will exhibit similar dispersion forces. Since CH3, CH2, CH3 is nonpolar, it may exhibit only dispersion forces. Because CH3O, CH3 is polar, it will also experience dipole-dipole attractions. That's what we said here, right? Finally, CH3, CH2OH, we didn't say it quite as succinctly as that. We should have. We should have just flat out said, hey, that's going to be polar because of that. And so you're going to have and it's actually going to be bent, right? So if we were to do this, it's basically like an oversized water molecule. And so we're going to have a negative charge here, and we have somewhere out here a slight positive charge, right? And so that's where you're going to get your dipole-dipole at. So this is London only, this is dipole-dipole, this is hydrogen, and so that is, we did correctly predict it, even if we didn't say, hey, it's dipole-dipole. All right, just to confirm, does it like what we have? All right, CH3, CH2, CH3 is our least, yeah, okay. Okay, well, let's do the next one. Let's do a similar one to it.
I think we flipped. It would be like the CH3, CH2 would be the negative 42, and then the other one is the 24.
Do it.
Yeah. Because the CH3 is the one that...
Ah, yes, 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 yes. Didn't catch that. Okay, thank you.
Let's see.
All right, my head got it backwards.
Okay.
All right. Well, let's do the next problem. Okay. Ethane, CH3CH3, has a melting point of negative 183 degrees centigrade. I can't write. Negative 183 degrees centigrade. And a boiling point of negative 89 degrees centigrade. Predict the melting and boiling points for methylamine, which is CH3 in H2. Let's start by drawing. Right? Here we're going to get the difference between these two, of course, is nitrogen. The big thing about the nitrogen is what?
The hydrogen bonds.
Hydrogen bonds that's going to form. So, all right, so if this one is negative 183 degrees centigrade for its, what is that? That's its melting point.
Yes.
Right, and negative 89 degrees for its boiling point. Is this going to require more energy to boil?
More.
Ballpark this.
Sorry, what?
Ballpark this. Give me a number.
I'd say like 39.
Okay.
Negative 39.
Okay. So negative 39 degrees centigrade, and how about over here?
100.
Okay.
Negative 100.
Negative 100 degrees centigrade. The most important thing is here is what are we thinking? Why are we thinking those numbers?
Because they're more energy.
It's going to require more energy to break those hydrogen bonds than it will to break these van der Waals forces. So, it says the melting point and boiling point for methylamine are predicted to be significant ethane, though they're similar size and mass, because the NH group may exhibit hydrogen bonding. The greater increases in its intermolecular forces, and therefore its melting and boiling points, is difficult to predict values, but the negative 93 and negative 6.
That was close.
Not bad.
39 was a bit of off.
That's not bad. That's not bad at all. All right. Okay. Properties of liquids. I'm now going to erase everything. Everything from here puts all of this into play. This is necessary to understand why everything else happens.
Okay.
Properties of liquids. The first property we want to talk about is viscosity. You're familiar with viscosity?
Yeah.
Viscosity is resistance to flow. Okay. So when we say high viscosity, what we're saying is it has a high resistance. It doesn't flow easily. That means that it's going to move slowly. So high viscosity is slow flow. Low viscosity is low resistance. It's fast flow. Water and honey, which one is high viscosity?
Honey is higher.
Honey and so how do we measure this? I mean, you could do it a number of ways. You could just like put two of them on a and turn the plate, you know, and see which one flows. That'll give you something qualitative, but we do have quantitative measures for this, and they really use two. One of them is you take a container and you fill it with a liquid, and you put a ball bearing right here, and you release it, and you calculate the time that it takes for it to fall. It's going to fall a lot faster through water than it is through honey. Okay, and the other is to put that liquid and just to see it run through a tube, and calculate the time that it takes. And that will allow you to calculate its viscosity. Intermolecular forces between molecules of liquid, their size and their shape and their temperature determine how easily a liquid flows. So viscosity factors. Okay, so these are intermolecular forces. And the size and shape of molecules. Temperature. Determine viscosity. Think about honey. Honey room temperature, high viscosity, low flow. But you heat it up enough, it's going to flow like water. Okay. That's all they want you to know about that. Cohesive forces. Are you familiar with the term cohesive? Co means?
Works together.
Together. Okay. So cohesive forces, the various intermolecular forces between identical molecules of a substance are called cohesive forces. The molecules within a liquid are surrounded by other molecules and are attracted equally in all directions by the cohesive forces within the liquid. However, the molecules on the surface of a liquid are attracted only about one half as many molecules as those on the inside because of the unbalanced molecular attraction surface of the molecules. Liquids contract to form a shape that minimizes the number of molecules on the surface. That is, the shape with the minimum surface area. You go into outer space and you take a syringe and you squeeze out water, right? On Earth, we do this and we're just going to get like this stream of water, right? That's going to fall to the floor. In space, I go zoot, okay? And I shoot it out. It's got kinetic energy. It's going to be moving, but very quickly, the intermolecular forces in it are going to cause it to form what shape?
drop,
like a drop, like a ball, right? If everything's stabilized, right, it's just going to form a perfect ball, a perfect drop. Because you've got these hydrogen bonds, these intermolecular forces that want to hold it together. The ones on the outside desperately want to be inside, right? So why a drop or a ball instead of like a long stream that's just connected? Well, that long stream, you've got a lot of molecules on the outside that are dying to be on the inside. And it wants to, the intermolecular forces are going to maximize the greatest number they can, and therefore it will contract. Is really all that this is describing. And we can see this. So you take water and put it on a waxed surface, right? First of all, the water, if I look at it like this, it's probably going to form this, right? It's actually going to defy gravity. Everything over it should, you would think, just go like something like that, or just spread, maybe even just spread out like this, just, you know. But it doesn't, because, and if I had the right molecule, maybe it would, right? If I had some non-polar molecule. But because I've got water and it's got a high number of hydrogen bonds, it's going to do this, right? They want to be as tight as they possibly can. Okay. Surface tension. Surface tension is cool. It's the cohesive forces at the surface of a liquid, right? So co is together. So the intermolecular force is holding a molecule together. I can take a cup of water and I can get it to bubble over, right? And the molecules at the top are linked together through intermolecular forces. And this is strong enough that I can float a paperclip on this. You know, this is classic freshman biology 101 floating paperclips. You can do it with pepper, right? Pepper will just float on the surface of water, even though it's denser than water, because of the surface. If I stir it up, it sinks to the bottom. But if I just sprinkle it on top, it'll just sit there, right? Okay. Bugs can move around on water and stuff like that because of surface tension. All right. Intermolecular forces of attraction between two different molecules are called adhesive forces. So adhesion. Okay. This has very low adhesion, very high cohesion, and so it bubbles up. This has the same cohesion, it's still water, but it has very high adhesion, and so it spreads out. So this might be something like a wax surface, right? And maybe this is something more like a plate of glass or something like that, where it's going to spread out a little more. Okay. Capillary action. I love capillary action. We're going to do a problem with capillary action in a second. So if I have a container of water and I put a capillary tube, I could put a straw for that matter, into my, by cohesion, whereas this is held together only by adhesion, and along the way it's helping everybody else. So this is capillary action. What do they want you to know about it? Yeah, I think that's pretty good. Let's do a problem with capillary action. The height to which a liquid will rise in a capillary tube is determined by several factors. So the height a liquid will rise capillary tube. Okay, there's a formula for this. It's H equals 2t cosine theta over rpg. So this is height equals 2 times the surface times the cosine of the angle of interaction. Divided by radius of the tube times the density of the liquid times gravity. Clear as mud? You write it down? Okay. So at 25 degrees centigrade, how high will water rise in a glass capillary tube with an inner diameter of 0.25 millimeters? Okay, and now it's telling us that the surface tension of water at this temperature is 71.99 m per m, and that my density should be 1.0 grams per centimeter cubed. Okay. Let's race over here and we'll do our math. I can erase all this, can't I? So my formula is H equals 2t cosine theta over rpg. Okay. All right, my surface tension 71.99 m. So what do we have per m? It's Newton meters per meter. That doesn't make sense. It says here the Newton is defined as a kilogram meter per second squared. And so the provided surface tension is equal to .07199 kilograms per second squared. Let's go ahead and try that one. So we get 0.07199 kilograms over second squared. Okay. The cosine here, so my angle is, we're assuming is 0. We're putting this thing in straight upside down. So cosine of 0 is 1.
I was straight, can't remember.
So it's this value times 1 divided by, we need to find our R, our radius. So what do we have for our radius there? Or our diameter is 0.25, so we need half of that. Right, so I can go 125?
Yeah.
Okay. Where are we at?
The density.
My density is 1 gram, 1.0 gram per centimeter cubed, right? And now I want to multiply that by gravity, which is going to be 9.8 meters per second squared. Okay. We're trying to get something in meters, right? Because we need height. So, okay. Everything's going to be okay, but we've got millimeters and centimeters and meters, right? And that doesn't work out. So let's convert real quick. Let's put 0.125 millimeters into meters, right? So what's that going to be?
We divide by 100.
0.00125 meters, right?
Yeah.
Okay, and this is going to be 1.0 grams per. Oh, that's not going to work out, is it?
Can you transform to kilograms? This is like up there is kilograms and then that cancels out.
Yeah, well, okay, so let's do that. Let's go to kilograms. So, how many grams is a kilogram?
1,000.
Okay, so this is going to be 0.001 kilograms per centimeter cubed, right?
Mm.
Now I need to get from centimeter cubed to meters, right? So how many centimeters, cubic centimeters are there in a cubic meter?
100?
Should be 100 times 100 times 100, right?
Yeah.
So what is that?
1 million.
So 1, 2, 3, 4, 5, 6. I'm going to add 6 zeros, right? Or I'm going to move it back 6 spots. Is that right? Or am I taking us down a hole? 1, 2, 3, 4, 5, 6, 1. And this is where we need scientific notation, because why are we doing this?
I don't think that's right. 1 gram per centimeter squared.
We went the wrong direction.
Sorry.
You all right?
Yeah, I was getting a calculator.
Okay. We went the wrong direction on our kilograms.
Okay.
We should have gone 1,000, like you said. Good here. Good here. Good here. This is the one we got to get to the right thing. Oh, they just flat out gave it to us. About 1,000 kilograms per meter squared is our value here.
Yeah. It's 1,000.
Per meter
Meter
cubed.
cubed.
Okay.
And then 2, it's missing the 2, it's 2t. Just put a t in full square.
I'm sorry, can you say that again?
It's missing the 2 on the left part. Yeah, it's 2t cosine, we just put it.
Ah, thank you. Okay. Okay. 2 times this divided by second squared times meters times kilograms per meter cubed times meters per second squared. Okay, let's, I'm gonna start crossing stuff out, making sure that our units match. So we got kilograms at the top, we're gonna get rid of kilograms. We've got second squared, we're gonna cancel second squared. We've got meters, that's gonna put me in meters squared. I got meters, that's gonna put me in meters.
That's right.
And that's per meter, but it's on the bottom. Is that not gonna be a problem? I have to find the inverse of this, right? No?
Yeah.
Yeah, okay. Okay. All right, let's do some math. So what do you get?
I got 0.0117.
How do we get from that to calculating our meters? Where my brain is going, I don't know what to do right now. It's that point where unitless flat out meters. How do we make that leap? I think I need this one.
I think it's because the T is now meter newtons per meter.
You don't like eating it? Yeah, I get tired of eating it pretty quick.
Ms. Smith, you got a second?
Yes,
How do we fix this?
what are we doing?
We're trying to get to meters. So everything we have is right. Our units cancel out and we're left on the bottom.
That's meters cubed.
Well, it cancels out to just meters. Right, 'cause it was meters cubed, but I got meters and I got meters, so meters times meters times meters.
Divided by meters cubed.
What is he doing hanging down there? Is it there a fraction bar?
We just,
Oh,
this is a biologist doing math, is really what this is.
oh.
So
What
we
is
just,
that answer supposed to be?
0.12 meters.
Can I
Yeah,
look at this?
yeah, that'd be great.
Because I'm looking at your biology going, I don't understand.
Yeah, I understand.
That's kilograms. And that's second squared over. And So that's gonna leave you with meters squared, and that's gonna leave you with meters.
Mhm.
And if you bring this over, you're gonna have kilograms per second squared over kilograms meters second squared. And if you invert that, second squared meters kilograms, you have meters.
I don't know what you just did. But I don't know what you just did.
Okay. Well, it's this idea, if I have 2/3 divided by 4/5, I can multiply
2/3 times 5/4.
But if I had 2/3 over 4 over 3 over 2, that's what you've got.
Okay.
You've got, this is a fraction, so it's more levels of the fraction.
Okay. Find that.
I'm just going to use the units and we'll.
Okay.
So I look at this and I've got, on the top, I've got kilograms over second squared. Just looking at units.
Yeah.
Then in the denominator, I have meters. I'm going to call that a denominator of 1.
Okay.
Times, then it's kilograms over meters cubed.
Mhm.
And then it's meter over second squared.
Heating up.
Good there.
Okay, so you got
Tanto difícil que necesitan los profesores.
meters squared kilogram over meters cubed second.
Hold on. You didn't put your second, right?
Right.
Okay, so hold on a second. Let me make sure of what I'm doing. You canceled that one
Oh,
out.
no, I just multiplied meters times meters and got meters squared kilogram
Okay.
over meters cubed.
Okay. I'm okay there.
Then that's going to be kilograms over second squared, kilograms over meters second squared, because you ended up with 1 meter down in the bottom.
Got it.
Now, you invert it, because it's a fraction divided
Okay.
by another
I'm
fraction.
okay with that.
So do I invert it? Second squared meters over kilograms. That took care of the bottom.
Okay.
Second
Now
squared.
let's cancel that. I'm not sure the numbers. Okay. Now I need to do that with my numbers.
Wow.
You don't have to stay for that.
No, you just need to
That's
let.
what I have to do. All right.
Ah! I had it.
I got it.
Right. I helped somebody.
I hope. We'll see.
Yes, come.
All right, let's
Oh,
go
here.
ahead. Thank you. Let's go ahead and do this.
My office.
All right. Of course.
It starts up.
All right. Okay, let's do it the way that yeah. I messed this up right here, didn't I? I messed this up right there. That was my fault. Okay, so 0.07199 kilograms per second squared over.
Oh.
Now we come in and she wants us to go, hey, you have 1,000 kilograms per
Meters squared.
meters cubed, right? Times 0.125, no, I'm sorry, that's wrong. 0.0025 meters over 1 times 9.8 meters per second squared. Okay, now at that point, this will cancel out, this will cancel out, this will cancel out, right? So let's condense all this. Okay, so I go 1,000 times 0.0025 times 9.8, right? And so that gives me let's go here, 0.07199 kilograms per second squared divided by 24.5,
That's meter per second.
and that's kilograms,
meter.
kilograms, meters, per second squared. Is that right?
Yeah. It's
Okay. Huh?
kilogram over meter second squared. Yeah, the meter.
Oh,
is
okay,
like-
I'm sorry.
Yeah,
Thank you. Okay.
and now when you go up, it's just.
Now, when I go up, I get 0.07199 kilograms per second squared times meters second squared over 24.5 kilograms. My kilograms cancel, my seconds cancel. I'm left with whatever this math is in meters. And so I go 0.07199 divided by 24.5, and I get, I don't think we have the right answer.
It's just because it didn't time 2 times.
Oh, I'll do it times 2, but I still don't think we have the right answer.
That's-
So we got to -0.12. All right. -0.12. All right. We'll pick up here next time. I'll have this problem down, Lord willing, and that'll be that, and we'll take off on looking at some other properties.
Okay.